Hello, and welcome to the next session of the Globe Summit, the Boston Globe's annual conference. Thank you for joining us both in person here in Boston and online for our next series of discussions, bringing the Globe's award-winning journalism beyond the page. I'm Aaron Pressman. I'm a tech reporter in the business section, and I'm moderating today's session on the promise of quantum computing. We have the most science fiction title of the day today, definitely. I'm pleased to be joined this session on the couch. I'll start from the far end. That's Mihir Bhaskar, research lead at Amazon Web Services Quantum Networking Center, which is not far from here. In the middle is Elton Zhu, director of quantum research at Fidelity's Center for Applied Technology. Is that right? FCAT. And closest to me is Shruti Bharadawa, global lead for in R&D at Sanofi and involved in some of the quantum stuff they're doing. So I think the first place to start when we start talking about quantum computing is to realize that even though it sounds like a science fiction concept, we have a lot of things today, lasers, MRI scans, which were all developed using quantum science. Quantum computers are a little farther off. Maybe, Elton, do you want to start by telling us a little about where we are in thinking about quantum computers and creating them so they're actually workable?
Yeah, so quantum computers work in a fundamentally different way than our traditional desktop computers. When we think of computers, like all your images, your Word documents, under the hood, they are all transformed into digital format of zeros and ones. But quantum computers work in a fundamentally different way. We typically say that they work in superpositions of zeros and ones, so they can be sort of 0 and 1 at the same time. So the operations that you can do on those quantum computers are fundamentally different as well. So that gives them elevated power to be able to solve some of the hardest problems much faster than our traditional computers.
And how close do you think we are to perfecting really usable quantum computers?
Yeah, that's a little bit hard to say. If we think of traditional computers, it starts in the 1950s, but personal computers only get widely available probably in the 80s to 90s. So we are still in the early regime of quantum computers, So it's just at the time that is going from labs into some of the startup companies to be commercialized at the moment. And I think it's still going to take a few years for us to see large-scale fault-tolerant quantum computers that can solve real-world problems.
Here at Amazon, it seems like you're focused a little more on a next-generation problem of once we have quantum computers, how are they going to talk to each other and network each other? Tell me a little about the challenge and what you guys are working on over there.
Yeah, so we're working on building quantum networks. And it is a next-generation problem, but I think it also has a lot of connections to the problems that Elton mentioned about scaling up quantum computers. And I like to draw back to the analogy of the 1950s and the invention of the transistor. A lot of the work that was done at Bell Labs was actually targeting how do you solve the problem of making long-distance phone calls. You had signal attenuation over these long distances. And so a lot of the research that went into inventing the transistor as we know it was actually in order to build amplifiers to connect these long distances. So actually that's one of the core problems that we're working to solve in our lab. When you have quantum systems and you try to make them larger and larger, especially over larger length scales, for example, if you want to use them for communication tasks or to connect up systems over distances, you have this problem of loss. And so what we're working on in the lab right now is building quantum repeaters that can actually serve the sort of quantum analog of an amplifier that allows you to connect systems over long distances with quantum signals.
And does it require the same kinds of technology that we see in quantum computers?
There's a lot of overlap for sure. So many of you who have followed the field are probably familiar with the pictures of golden chandeliers and other shiny things. There's a lot of that kind of technology like cryogenics that's required to cool down a lot of the materials we use so that they actually operate in a quantum way. But I would say there are also some new technologies or different technologies, particularly related to lasers, related to optical, high-speed optical components that are have a bit more overlap with what you would see in today's conventional data center switches, routers. Those are the types of technologies that we really need to engineer in a way that's compatible with quantum technologies to realize quantum networks.
Thank you. Shruti, I know you're a little more removed from the technical developments, but tell me, Sanofi is interested in quantum computing. Why?
Well, we do think it is something that's going to happen. We do believe, I mean, as I think both Elton and Mihir touched upon, and so did we in the green room, AI has been something that Sanofi has been very focused on. So we would like to see how this goes. But right now, and quoting what Elton and Mihir just said, I think we are a little far from actually using quantum computing for the things that we do right now.
Well, take us a little into the future. If quantum computing comes to bear, how is it going to help Sanofi?
I think the core problem that quantum computing may help us would be optimization problems, right? So especially for drug discovery. So when we think of drug discovery within any pharma company, right, we have specific molecules that we are trying to identify. This is a clear optimization problem. For us, within the pharma company, I'm not just talking Sanofi, but Novartis, Sanofi, Roche, any one of these pharma companies, for a single molecule, it takes about 10 years.
10 years?
Yes. So the hope that we have with quantum computing is reduction of this time and also the cost, right? So 10 years of trying, it's almost hit-miss, sort of a cycle that we go through for drug discovery. So if we can optimize the way we look for drug candidates, I think that would solve quite a bit of a problem. But we're not there yet because the infrastructure isn't there yet.
And I'm curious, I think maybe for all three panelists, one of the reasons I think that quantum computing has taken hold in Boston is because of the academic strengths we have here. So maybe if each of you could talk a little bit about how do you interact with the big universities and colleges here and how maybe that's helping on quantum.
Yeah, I can start. So I think in Boston, there's a very good local ecosystem. We have some of the very great universities that are producing excellent graduates, including some of us, I think. And some of them like even go out to start a lab or like found a startup company. So that's helping the ecosystem to grow. You know, as a company, we are actively engaging with them just to see what technology they have, whether we engage them from academic collaborations to like proof of concept, just trying to solve some of our internal problems.
Yeah, I would say quantum computing and networking, any quantum information technology, is still at the stage where, yes, there's a lot of engineering challenges that industries are starting to solve, and those are required to make progress. But we also don't have a blueprint on how to realize any of these technologies. So there really are fundamental research questions that are better tackled or more efficiently tackled and are being tackled at these universities. And so we realized that at AWS, and it's part of the reason why we started a research alliance with Harvard, because it's one of the leading institutions actually in quantum networking. A lot of the pioneering technologies on platforms to build quantum repeaters were built at Harvard. And so the research component is really important, and that's one of our thrusts of our alliance. There's a couple of other components, and they're more related to sort of very specific training and education. And that's also really important because there isn't a large workforce of people who can actually come into the field and contribute directly to quantum computing. For the most part, you're talking about physics PhDs, which is an extremely limited subset of people. And if we want to make progress in the field, we need to have a larger workforce who are contributing. And so that's why part of what we do in the university is also to provide funding for new tooling, for training programs, and also for scholarships, both for your traditional kind of scientific background and also for more engineering-focused approaches that would potentially get people into the field without having to get a PhD in physics.
No, I echo what Mihir said. I think when we think of quantum computing specifically, there's no degree in quantum computing. Such a thing does not exist. So we go with physicists, right? That's our mathematicians. But for Sanofi, I can speak. So we do, collaborate very much so with external partners, especially the academic institutions. So we have an award system where we award sort of an initiative where we encourage academic institutions to pitch in their proposals. And most of these are very AI focused. I haven't seen most quantum yet, but they're very much AI for drug discovery, AI for clinical trial design. So we do see a lot of this, and we do hope to sort of integrate some of these into Sanofi. Right? So.
One of the things that some of the startups in Boston have been pitching to me is that we don't even need to wait for quantum computers to start thinking about using some of the techniques in our software maybe to enhance how we're doing things and make it more efficient today. Certainly in AI and generative AI, I've heard a lot about this. I'm curious if any of you have started dabbling at all or working with software simulations before the hardware is ready.
Yeah, I think for our team at Fidelity, so like our first step in trying out a new hardware is just to check if there's simulator software that is available for us to use, and we make sure that our every project that our tools are like readily available to switch between simulator or hardware backends. And actually, for the moment, I think some of those simulators are still probably a little bit better than the hardware backends because the hardware still have considerable noise. Yeah.
Yeah, I think that's absolutely correct. I think it isn't clear yet that there's any benefit at this stage to use quantum computing or some hybrid classical quantum solution, but there's a lot of interesting active research in that area. On the networking side, not specific to software, but what you can do today with the hardware that we actually have the ability to transmit quantum states over, on the order of 100 kilometers, where you don't need a repeater. You can actually transmit a signal over a fiber optic cable from point A to point B. And that actually allows us to already build some test beds, build some of the supporting infrastructure, the types of laser systems, the modulators, the detectors that would go into a long-term quantum network. And there's interesting research that you can do in privacy and security of these communications channels. And so this is an active area of research. Whether it will have a major impact in the near term to industry and businesses, it's not something that is currently being actively pursued that much in the US. It's something that we're seeing a lot more of in the EU and in China. But it is something that we can do today with quantum networking technologies.
I think for the pharma, we haven't completely explored the option because I think it's still, we are at a stage where we are educating people. We need to understand what quantum computing actually means to even design our infrastructure, design our systems, design our algorithms to sort of be hybrid. So it could go both classical computing as well as quantum. So I think that's where we are in terms of just educating people, understanding what this is.
Got it. Mira, you just mentioned the word privacy, and I think one of the questions we have from the audience is, we think of quantum computers sometimes as just they're speeding things up and they're doing calculations more efficient and quickly, but there are other aspects of it. Talk a little bit about some of the other aspects of quantum besides just super fast computers.
Right. Well, there's two sides to the coin. So I'll first say one more thing about super fast computers. And actually, one of the algorithms that got people really excited in quantum computing is an algorithm called Shor's algorithm. It actually is a quantum algorithm that allows you to factor a very large number into two primes much more efficiently than we can do with any known classical algorithm. And that was surprising because that hardness of that problem is actually what a lot of our old cryptography systems were based off. The assumption that no one could break that problem.
So that's, when we're sending information to the bank on the internet, we're using encryption that relies on that kind of math.
Some of the old, I think people are starting to transition to what we believe are more and more robust algorithms. But there's the possibility that quantum computers could, because they can solve new problems that we haven't had access to, that they can now break some of these algorithms. So in terms of privacy and security, that's where we see one of the opportunities of quantum technologies, in particular quantum communications technology. If you're transmitting, if you can share quantum information between different endpoints, you can actually perform an operation that's called quantum teleportation.
Teleportation.
It's unfortunately not as exciting as it sounds, although it does have a very science fiction name. But from a privacy and information theoretic security point of view, it is very exciting because it means you can actually transmit individual quantum bits of data. So this can be information, it can be a secret message, without ever having to actually send that message over a channel where it could be intercepted, it could be stored, et cetera. And so there are implications in the long term for privacy, especially when we're talking about, when our information is distributed everywhere, whether it's on our devices, whether it's in the cloud, and there are a number of third parties that might have access to it. The ability to use quantum teleportation could be very influential if we can make it practical.
Elton, we haven't really talked about why Fidelity is interested in quantum. What are some of the applications that you're exploring?
Yeah, that's a great question. So in Fidelity, we solve a lot of computationally hard problems, for our fund managers, for our customers. Some of them like portfolio optimization, like how do you build a portfolio of maybe 500 stocks that has the best risk-return characteristics, or how do you do a retirement planning for your customers, simulating all the possible scenarios. These are fairly computationally intensive problems, and we believe that quantum computers, once they are in full power, they will be able to solve these problems much faster. And by solving them much faster, you may say like, it may not sound that exciting to you. But we think that when you are solving certain problems faster, it opens up new business capabilities. It may allow us to offer new products to our customers as well. Yeah.
One of the things that I was really impressed with, talk about how much more quickly you could run those kind of simulations, right? Something that you could maybe run it in real time. Is that right?
Yeah. So firstly, I just want to clarify that in our team we explore not only quantum computer but other computing technologies as well. So we believe that using the most advanced computing technology, you can solve some of the Monte Carlo simulations in almost real time. That allows like real time risk analytics, for our portfolios. Yeah.
And the stock market is not hanging out waiting for your answer to come. So
that's not for me to comment.
Shruti, talk a little bit about, I know quantum is early for you, but you're also very involved, Sanofi is very involved in AI. Can you talk a little bit about some of the new applications that you're thinking about?
Absolutely. So in Sanofi, we have sort of started this initiative where we are integrating AI in every aspect of what we do, whether it is portfolio, and I spoke about sort of drug discovery and using AI for drug discovery and clinical trial design. I think Sanofi's strategy here is to partner with experts in the field. So we have partnership with Okin, we have partnership with Atomwise in silico medicine. So I think the idea here is to see how we can partner, how we can leverage each other's strengths, and then sort of see how we can bring in AI into Sanofi. So we have all of our portfolio decisions are made using AI now.
It's a new world. Now, we've learned, unfortunately, that all technologies have both positive uses, but also sometimes negative uses or risks. I'm curious for each of you, are you thinking about scenarios where we might need to change the way we do things, for example, if encryption was cracked, or other things that you're thinking about as risks maybe from quantum computing?
Yeah, I think in my mind, that's the biggest risk is when we enable this new potentially toolbox, computational toolbox, we need to think about also what are some of the kind of the implications of that. For example, what are we relying on that we cannot compute in with today's computers? And for me, encryption is the biggest thing that we need to be aware of. And there is actively, and AWS is participating in this process. There's an active process being led by NIST to standardize a new set of algorithms for cryptography that we call post-quantum cryptography.
Post-quantum.
Exactly. And the idea there is that, okay, well, we know the theory of quantum computers. We know a handful of possible algorithms with quantum computers that might expose some of the previous cryptography algorithms we've used. So it's really taking some of the best mathematicians and trying to come up with new hard problems that we believe will still be challenging to implement even when we have fault-tolerant quantum computers. So that's really important. But one thing to be aware of is that whenever you have these new kind of unknown algorithms, it's really complicated math that a very small subset of experts around the world really understand. So there is always some risk that you can find backdoors in these algorithms. So it's really going to require a kind of community effort to ensure that these algorithms are well vetted before they're actually implemented in production systems. And AWS is developing some of these PQC algorithms, and in sort of trial basis, they're already available in some of the services that we offer. But this is very much something that we believe, in addition to technologies like quantum communication, which might be a longer-term solution that don't rely on encryption, PQC as a software upgrade is definitely the first step towards preparing for quantum computers.
Anybody else thinking about implications?
Yeah, I think one of the biggest, like as Michiel said, like one of the biggest implications of quantum computing is the encryption system. And for us, there's one thing special that requires to pay a little bit more attention, which is the blockchain system. So at Fidelity, we have a great digital efforts to offer this like blockchain tokens to our customers. And some of these blockchains rely on encryptions that are vulnerable to quantum computing. And we actually hold a talk which is discussing the threat of quantum computing to the blockchain ecosystem. And some of the older Bitcoin wallets, they're pretty susceptible to quantum computing. The fast algorithms. So I think regardless of whether other encryptions, digital signatures or blockchains, they have to start thinking about how to transform into post-quantum encryption standards.
Shruti, for AI or quantum, are there areas where you're a little more worried than promising?
No, so I wanted to go back to the quantum. So for us, we're not there yet. So we're not where Fidelity is at this time. But I think if we do choose to go with quantum, I think the entire security infrastructure needs to be addressed, right? It needs to be changed. It needs to be robust to allow quantum computing. But other than that, I think for us, the main security is we deal with patient data. We deal with human data. So I think it's important that we make sure our security is top-notch. So I don't think we have any free space there. Right. So in terms of security, I think what we have, especially that we have AI sort of leading the way for drug discovery as well as clinical trials, as well as everything we do, I think it's very important that we have a governance system, of course, that sort of keeps track of how this is going. Compliance is a big thing for us. So I think these are key things that Sanofi sort of is focusing on at this time.
You mentioned sort of the global picture too. Do you think the United States is keeping up in quantum, or how would you compare us to other efforts around the world?
Right. I think we're certainly competitive in quantum, but I think competitive is the key word. I wouldn't say we're clearly leading the way in quantum. So I think the unique thing that the US has is that we have major technology providers that are actually investing significant amounts in actually building quantum hardware, and that's actually pushed the field forward significantly. But if you look at the state of the art of research and the amount of investment in quantum around the world, when you look at the EU and you also look at China, there are major investments. It's hard to validate all of the numbers that you hear from various companies, but more than $10 billion of investment in quantum technology worldwide. We believe.
Over what time period is it?
I believe this is over, off the record, since I'm not sure, but I believe this is over, over the last 5 years, new investments in quantum technologies. And so if you look at the amount of investment that there is worldwide, and the fact that there are some applications of quantum computing that could have security interests, it really does start to become a national security interest. And we have seen this in the latest sort of measures from Congress. There has been quite a bit of new funding in the United States for quantum computing and information technology research. And so I think that will continue to actually be key because there's still a number of fundamental research problems. Quantum computing is not likely to pay for if we talk about this $10 billion number, it's not likely to pay for itself until we have really fault-tolerant quantum computers, which could take a decade, if not longer. And so this continued investment from the public sector is going to be key, and that's actually being driven by the fact that there is so much competition around the world.
One thing I wanted to ask all three of you, you're each part of very large, established organizations, but we're talking about technology that's on the very cutting edge with small startups and little labs all over the world. I'm curious for each of you, how do you keep up with the field? Maybe, quantum and other things that you need to stay on the very cutting edge. What are you relying on? What resources, what methods?
Meeting people like Meir and Elton, right? I mean, I think just meeting people, connecting with people, conferences, I think these are the key things, right? So this is where discussions happen. This is where ideas come out. I think that, for me, yes. So I will follow up with me here after this, but yes.
Yeah, so for us, like at Fidelity, we pay a huge attention on disruptive technologies. Actually, like our business group, like Fidelity Center for Applied Technology, you may not know, is founded more than 20 years ago, just because our CEO do not want to see another Y2K coming and disrupt everything. So for us, we have dedicated teams looking into quantum, looking into immersive technologies, looking into blockchains, fintechs, and we have even researchers looking into like social economic trends and how that affects the like our future generation of customers. So we have a whole dedicated team that is looking at different kinds of disruptive technologies and how our firm can leverage them in the future.
And for us, providing the best computational resources at scale is kind of the core of what AWS does. So it's a very natural area where customers who use the traditional cloud are asking us how this is going to affect their business. And so we need to innovate on their behalf, and we need to be leading that in order to be able to answer those questions and then eventually provide the services that they'll need when it comes to quantum. That's one side of the story as it relates to quantum computing. As it relates to quantum networking, privacy and security are priority number one for AWS, the privacy and security of our customers' data. So making sure that we're staying ahead of any potential threats and also investing in the sort of leading edge technology to ensure that privacy and security is a no-brainer for us, even though we know it's a long-term investment.
So through AWS, customers can access a variety of different quantum computers. Do you have any sense of sort of what's in the lead, or if the different technologies are all still very, very early?
Right. So we don't break out information about what our customers are doing on AWS, but I can tell you the fact that we offer access to so many different types of hardware platforms, whether it's superconducting circuits, which are perhaps the most common technology for building a quantum computer, or individual trapped ions or neutral atoms. What we do see is that when we bring on new quantum hardware providers, we see really spikes in interest to try out these new hardware platforms. And as Elton mentioned, a lot of these systems are a lot worse than if you just break out your laptop and you simulate it on a classical computer, right? And that's because these systems are currently noisy. We haven't figured out yet how to overcome noise. But I think one of the things that's really cool about being able to experiment on this hardware, if you look at the papers that are being published, in the last 5 years, numerous papers have been published, learning about the physics of what's happening on these quantum computers, just based on being able to try them out and use them over the cloud. So I think this is an extremely powerful tool. It's not going to be solving, important problems for Sanofi or Fidelity or other businesses until we overcome those challenges with noise. But it's a really important tool for researchers who are trying to figure out, how to make quantum computers better, and also, what things we might be able to use them for in the future.
I'm curious, Elton and Shruti, for your companies, do you think ultimately it's something where the companies will have their own quantum computers, or is it okay to rely on, external hardware?
This is a very good question. I think this really depends on what is the progress of quantum computers and when we will see large, stable quantum computers that will justify purchasing one. So in the near future, we think that maybe cloud access is still, maybe through AWS, is maybe one of the best ways to access quantum computers. Same as we have access to some of the AI chips through the cloud as well. If you buy them, it's going to cost a few $1 million. And for quantum computers, just because the field is progressing so fast, if you buy one, 1 or 2 years down the road, it's probably going to be obsolete. Yeah.
Shruti, same question, and also on AI and quantum.
I think I echo what Elton just said. I think we're experimenting, so it takes a lot of infrastructure cost and everything. So unless we know it's something that is usable for us, unless we know it's something that we will be continuously using, I think partnering with startups, partnering with AWS, for example, having that cloud infrastructure, I think would be beneficial.
Do you think for AI, is it more advanced? Are you doing, do you call up NVIDIA and say we need some more chips?
Well, even for AI, at this time, Sanofi is partnering, right? So internally, what we have decided is we would like to partner with, and I mentioned Atomwise, I mentioned Insilico, I mentioned Oken. So there are a lot of companies like this that are doing, really groundbreaking work, as in they're the experts in what they do, and we're trying to leverage what they can offer. So I think that's sort of the strategic view that Paul Hudson has, so we'll stick to that.
Okay. We're running down on time. We can take questions from the audience online or from in the room if anyone has one. I'm interested in how when you're at a dinner party and someone says, "What do you do?" Let's hear everybody's explanation of what's the dinner party line on quantum computing.
Well, the one sentence answer is I shine lasers at diamonds. That's the research that happens in my lab, and then I like to take it from there. But I'm interested to hear what others have to say as well.
I would say that I'm programming a computer that is 20 years into the future.
I don't usually use quantum computing to introduce what I do. So no, I make drugs for people.
You make drugs for people. Very good. I think we have a question over here.
Do you mind delving into the example that you gave where there could be communications that aren't actually being transferred over a network, and what does that actually look like, and from a business perspective, how would that be leveraged in the future?
Right. I'll answer the last part of the question first. Is we really don't know how this is going to be leveraged yet from a business perspective, and it depends on all of the implementation details. But regarding the implementation, it's a protocol known as quantum teleportation, which has been around for more than 20 years. And it leverages the fact that quantum particles can be in this unique state that we call entanglement, that we describe with entanglement. And this is the phenomenon that famously puzzled Einstein. And it's basically if you have two individual quantum particles that are entangled, and you measure one of them, the other one is always in the exact well-defined state determined by the first one. So
even if they're far.
Even if they're very far on other sides of the universe. And so, if you just have one of these particles, you might be measuring noise, 0, 1, 0, 1, 0. It means nothing. But your counterpart on the other side of the world is also measuring the exact same thing. And so that's a pretty unique phenomenon. It doesn't exist in any classical technology. And so if we can share these entangled particles as a resource to parties that want to communicate, or even two parties that might have individual quantum computers, they can actually use this information to encode and teleport messages or data directly to their counterpart without having to actually send what they're encoding in any encrypted or plain form. So that's a sort of new way of communicating. There are caveats. You can't do this faster than the speed of light. No communication that we know of happens faster than the speed of light. But it does have implications for privacy, especially in fields where there's regulations about where data can live. We see a lot of our customers still have to maintain their IT infrastructure. Even if they come to the cloud, certain parts of that still need to live on their secure premises. And so if you can actually directly connect two secure, trusted locations without having to send data across it, then this can be transformational for those kinds of use cases.
And when you say send, what does that look like, I guess?
Yeah, so in the case of...
We just have like a little bit.
In the case of teleportation, you'd have to share this entanglement, which would be just like a resource, like a utility that you could distribute over fiber. And then the end customers would need some small quantum computing devices where they can actually encode this information and then read out the results.
Like a walkie-talkie.
Kind of like a walkie-talkie, yeah.
Well, we'll have to leave it there. Thank you so much. It's been a pleasure talking about quantum computing. Thanks to our panelists today for all their insightful commentary. There's a lot more great sessions coming up on our theme of today's innovators, tomorrow's leaders, which I think we definitely hit on today. So be sure to keep watching. And a quick reminder that Globe Summit sessions are being recorded and will be made available for viewing after the event. Thanks for taking part and being part of our community, and enjoy the rest of the event.